Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is deformation behavior of honeycombs and foams. In the last lecture, we learnt about several aspects of the deformation behavior of honeycombs. Especially we learnt about the in-plane deformation under compression and tension, and then also we learnt about how deformation typically propagates under in-plane deformation when a honeycomb is compressed by external load, and also we learnt about the aspects of elastic deformation and brittle fracture. The main topics to be covered in today's lecture include effect of structural defects during in-plane deformation of honeycomb materials, then out of plane deformation, and after that we will learn briefly about the deformation behavior of foams, where we will mainly learn about the elastic deformation under compression behavior for elastoplastic materials and also the aspects of linear elasticity of open cell and closed cell foams. The main keywords for this lecture are in-plane deformation, out of plane deformation, compressive behavior, elastic deformation, linear elasticity, open cell foams and closed cell foams. So, let us start with the in-plane deformation behavior of honeycombs and the effect of structural defects. Now, as we learnt in the last lecture or also in some previous lectures, that honeycombs are actually regular array of hexagonal cells arranged together, and these cells when they are applied or when they are compressed in the in-plane direction, then the yield strength and the Young's modulus of the honeycombs are actually lower than when the honeycombs are actually compressed along the out of plane direction. The out of plane direction is nothing but when we apply the force along the thickness of the honeycomb, while if we apply the force along the length or breadth of the honeycomb structure, that is the in-plane direction. We also learned that when such a honeycomb is actually compressed by external loading, then the deformation actually propagates in the form of deformation bands. These bands initially they initiate at a location of at a weak location, and then the cells which are very close to the initial defect in that band, they actually deform initially, and then as we deform the honeycomb more and more with more external compression, more cells actually join the band and the band actually propagates. But whatever we learnt in the last few lectures about the deformation behavior of honeycombs, they were mainly about the perfect honeycomb. That means that it was assumed that the honeycombs have a perfect structure and there are no defects inside the material. But as we know, real structure always have some defects or some anomalies, and these actually reduce the strength of the material. In case of honeycombs, the same thing also happens, and in this slide, as you can see over here in this honeycomb image which is being shown over here, there are many such locations where one or two arms of an hexagonal cell are actually missing. So, these you can see in this inset image which has been kind of extended for better viewing. You can see that many of the honeycomb arms are actually shown by the dotted lines, and these dotted lines are actually the locations where some defect is there, and that means the honeycomb arm is missing. And this analysis was performed by June et al. By simulation. So, what we can see is here the influence of these missing arms or the defects on the Young's modulus and strength of the honeycombs was analyzed, and as you can see over here on the left hand side, it is the effect of the residual modulus. That is, the residual modulus means the modulus of the honeycomb with the defects present divided by the modulus of the honeycombs without any defect, that means the perfect honeycomb. And on the right hand side, the image is the residual strength, that means the compressive yield strength of the honeycomb with defects and divided by the compressive strength of the honeycomb without any defect. and the x axis actually shows the residual or the reduction in the relative density. This reduction in relative density is nothing but, that means as we imagine that if we reduce, that means if we assume that some of the honeycomb arms or the sides of the honeycombs are actually missing, that will actually mean that the density of the honeycomb is actually decreasing, right, because we reduce, we omit the material, some materials, or we remove some materials, and that is a defect in the structure. And in these plots what we also see is that what is the effect of this reduction in density on the relative modulus and the relative strength of the honeycomb structure. In these images, the curve which is marked by intact, that is actually the drop in the material property, both strength and modulus, for perfect honeycomb. That means in these cases where the intact curves are being shown, there are no defects in the structure, and whatever reduction in density is actually occurring, this is because of your kind of cell wall thickening, because as we know that the density of the honeycomb, as we already learned, that the density of a honeycomb, it means rho over rho star, is actually it is a function of your T and L. That means the T was basically, as we learned already, the T and L are basically the dimensions of the honeycomb cell wall. That means if we assume that the honeycomb structure has no defect in it, but only the thickness of the cells or the thickness of the sides are decreasing with respect to the length of the honeycomb or honeycomb cell, that means a perfect honeycomb but with lower density. And as we also know that the properties of the honeycombs are actually dependent upon the relative density. So, these will actually show that with decreasing relative density, even for a perfect honeycomb, the properties will reduce. That means both modulus and strength will reduce even for a perfect honeycomb when the density actually decreases. However, then in both the curves, the lines, the curves, that means this curve, these two curves that are being shown over here, these two curves actually show the property of the honeycomb in the presence of defects. That means now what is happening? Again the density is decreasing, but at the same time this density decrease is because of the missing arms. That means it is not because of any perfect honeycomb anymore. Now we are actually systematically that it is assumed that some of the arms are defect, and that defect arm will actually render lower density to the structure, and how that will actually affect the properties. So, what we can see here is that we can see that already at only 5, that means this point, as you can see over here, this point corresponds to about 5% density reduction. That means because this is the 5% line over here, that means both these lines, that means this is actually assumed that at this point 5% of the cell walls are actually missing. And as you can see over here that already there, I mean only 5% of missing cell walls, they already cause a property drop. I mean you can see on the y axis, they already cause a property drop of already around 30 to 40%. So, you can see the defects are so insidious. I mean the presence of defects have a very bad effect on the properties, and only 5% defects reduce the properties significantly. And if we keep on increasing the amount of defects, that means as you can see, when we reach around 30% defects, we see that the properties are almost 0. That means when 30% of the honeycomb arms or honeycomb cells are actually missing, then there is no modulus and no strength, and the properties have actually achieved the value of 0 theoretically. And this actually also follows the percolation theory, because according to percolation theory it is said that when a material has around more than 35% of defect, then there is actually a continuous path through the structure and the structure will lose its stability. So, this is actually one very important aspect, that if the honeycomb structure is not perfect, as we know that all real materials they have some defects, then it will have a significant bad influence on its mechanical properties. The other way around, if we just assume that now all these honeycomb cells they are actually void, that means it is a hollow cells. Now, if you assume that then some of these cells are actually not hollow, rather they are kind of filled with material. That means it may happen that because of some fabrication process, or we can also do it intentionally, that some of the cells are actually not void, rather that's a opposite sense of having defects in the structure, that the cells are actually filled with some material, and these will have the opposite effect of the defects in the structure. In these cases, when the cells are filled up with materials, we will actually have a higher strength and modulus. So, again that means the influence of the structure on the honeycombs are very important. If there are defects in the structure, like in these cases when we have the missing cell walls like here or here, when the cell walls are missing in a random fashion, then they will have a negative influence on the properties, both modulus and strength will decrease, and already at 5% missing cell walls the properties will reduce by almost 30 to 40%. Other way around, when we keep on filling up the cells, it will have an opposite effect, and the properties of the honeycomb will increase, both modulus and strength will increase as the amount of material inside the honeycomb cell walls actually increases. So, all those discussion what we have learned so far, this was about the in plane deformation of honeycombs. So, as we already know that in plane deformation means, I mean if we again see these diagrams or these images over here, a honeycomb has two in plane directions. That means in this case the x1 and the x2 directions, they are the in plane directions, and the x3 which is along the height of the honeycomb, this is the out of plane direction. And we already learned that that also along the x1 and x2 direction, when the honeycomb is deformed, the strength and the modulus of the honeycomb also depends upon the dimensions of the cells. If all the edges, that means this, if all the edges are the same size and the angle between the two sides are around 120 degree, then we know that the honeycomb is an isotropic material and the properties are identical along x1 and x2 direction. However, if the cell edges are of different dimensions or the angle is different from 120 degree, even in that case we will have again properties will be different along x1 and x2 direction. But it is important to remember that even though the properties might be different along x1 and x2 directions, the properties along the x3 direction, that means the outer plane direction, will always be highest. That means we will always have highest strength and stiffness along the thickness of the honeycomb, and this is because when we compress the material, because compression is the most important deformation behavior for such cellular materials, when we compress along x1 and x2 directions, the only deformation that happens is the bending of the cell edges, right. But when we compress along x3 direction, there is also tension and compression of the edges apart from only bending, and because of that, because of this compression of the edges and the thickness direction, there will be more resistance to the structure to the applied load, and as a result of that we will have higher strength and stiffness when the honeycombs are compressed along the thickness direction. And along thickness direction also the number of moduli will also be different. So, as you can see over here, when we compress along the x3 direction, we will have one Young's modulus, that means there will be one modulus, that is the E3, and there will be two shear modulus and two Poisson's ratios. So, in total when an honeycomb, I mean for an honeycomb structure, around 9, I mean even if it is an isotropic structure, 9 elastic constants will be required. That means 4 in the in plane direction as we already learned, and 5 along the out of plane direction. Now, this higher strength and stiffness when the honeycombs are compressed along the outer plane direction is extremely important for many applications, like for aircraft panels, skis and etc., where those big panels actually they are made up of face sheets. That means the honeycomb structure actually you will have this honeycomb structure in between the face. That means the honeycomb structure is like this. This is the outer plane direction, and this way the load will be applied along this, typically bending load is applied along this direction, and this will actually provide extreme amount of specific bending strength and stiffness, which is not possible when we actually make the honeycombs or load the honeycombs along the in plane direction. So, this was all about the deformation behavior of honeycombs. We learned several aspects, and next we will discuss about the deformation behavior of the foams. and there we will differentiate between open cell forms and the closed cell forms, and also we will differentiate between, as we did for the honeycombs, about different material behavior like elastic material or elastic plastic material, and also ceramic materials which are brittle materials. Okay. So, as we know we learnt about the honeycombs, that the stress strain behavior of honeycombs had 3 regions, the compressive stress strain behavior. The 3 regions were, initially we had the linear elastic region, then we had the long plateau region, and then we had the densification region. And the same 3 deformation regions are also present in the compressive stress strain behavior of the foams. The difference between foams and honeycombs should be clear by now, as we learned already. While honeycombs are basically kind of 2D regular structure, in case of foams the arrangement of the struts, and it is kind of a polyhedral structure in 3 dimensions, having struts and faces which make the edges and faces of the cells. So, this is basically a foam structure. And as you can see over here, in case of in case of foams also we have 3 different regions. Initially we have, in case of elastomeric foams, we have the linear elastic region where the deformation is happening, or what this in this region for elastomeric foams, it is the elastic bending of the edges, and then we have a very long plateau, and this plateau is basically defined and in this region, this long plateau region, the main deformation is the elastic buckling, right, for elastomeric foams. And then when the deformation achieves a very high amount, which is given by this epsilon d over here, this is called the densification region, where the opposite cell walls are actually touching each other. But in case of elastomeric foam, it is to be remembered that this deformation behavior is continuously, it's elastic in nature, but it's not elastic, it's not linear elastic anymore, it's non-linear elastic. That means if you remove the applied stress, it will come back to its original dimensions, but the behavior will not follow a linear straight line as per linear elasticity. The middle curve that we see over here, in this case we have the situation is called the stress strain behavior for elastic plastic foams, typically observed for metallic foams especially. And here again in the elastic region we have the elastic bending, and that will give rise to this linear elastic slope. But you will learn afterward that the E modulus of the slope, or the E modulus of the material which we obtain from this stress strain behavior is much lower than the actual E modulus of the metallic foam, and these are there are different reasons for that, we will learn afterward. And then after we reach the plateau stress, we have a very long plateau. In this case we have the plastic yielding of the material, as you can see over here, and then again after some amount of deformation we have the densification region. In case of brittle material like the ceramic materials, again we have initially the elastic region which is following the linear elastic fracture mechanics, and then after we reach the plateau region there is actually the brittle crushing of the material starting over here, and starting from this point individual cell walls or cell edges actually they break off, as we already seen for the honeycombs, they start breaking off, and when they break off they actually crush the structure. That means the whole structure gets crushed off, and the stress required for continuous deformation is continuously increasing until we reach the densification strain, as shown by this epsilon d point here once again. So basically as you can see this again for open cell foams, again the thing is that again the deformation is much more simplified, because in this case we have only the buckling and bending of the cell edges. But in case of, if it is a closed cell foam, then we know that the closed cell foam has both cell edges and the cell faces, and when we actually compress, then what is actually happening when we are actually compressing, then it is not only the bending of the cell edges, it is also the stretching of the cell faces, and because of the stretching of the cell faces, that will actually give rise to more strength and more modulus, and that is why the theoretical strength and modulus of the closed cell foams should actually be a bit higher than the open cell foams. Now this deformation behavior of the open cell foams has been explained rigorously by Gibson and Ashby. They have assumed this kind of ideal cubic structures, or cubical cell structures, where the cells have been assumed to have specific lengths of L and thickness, or the cell edge thickness of T, and then this again this T by L ratio over here, this that means this T by L is actually, as we already know, it is proportional to our rho star over rho s, which is the relative density. That means again, as we already learnt at the very beginning of this lecture, that for cellular solids one of the most important properties is the relative density of the material, and this is according to Gibson and Ashby theory. They actually take this or they actually take care of this relative density by varying the ratio of the T by L, which is the thickness of the cell edges to the length of the cell edges. And as you can see over here, when such a material, when such an open cell material is loaded from by external loading, as is being done here, then there is actually undergoing elastic bending is happening. That means the midpoints of the cells undergo deformation, and we can actually, by simple beam theory, Gibson and Ashby have actually proposed the expressions for elastic modulus based upon the relative density. And for open cell forms, we can see over here, this is a very simple relation has been proposed for the elastic modulus of the open cell materials based on the relative density of the forms, and C1 is a constant which is a value close to unity. That means we can see here E star is the modulus of the cellular solid, Es is the modulus of the solid at the cellular solid, and the rho and rho over rho s is, as we already discussed several times, it is the relative density of the open cell form. That means if we can measure the density of the open cell form precisely using the techniques we already learned, we can actually predict the modulus of the open cell form using this simple equation. And the expression for the shear modulus has also been proposed, as we already know that shear modulus of the materials are lower than the elastic modulus or the Young's modulus. So, here we have the similar expression, but we have a different constant C2 whose value is approximately 3 over 8. And using this combine, I mean when we combine these two expressions, because for the cellular solids we need if the material is isotropic in nature, that means all the properties are same along all the directions, we need only two moduli, and that means if we know only Young's modulus and shear modulus, we can calculate the Poisson's ratio from there. And as you can see, for cellular solids, Gibson has actually proposed that the Poisson's ratio is actually not dependent upon the porosity, and it remains more or less constant at around 1/3. That means basically the Poisson's ratio of the cellular solids is, I mean according to Gibson Ashby model, it is very close to the Poisson's ratio of the bulk material of which the cellular solid is fabricated. However, there are some design aspects which have been proposed to also make materials which have negative Poisson's ratio. As we know that the Poisson's ratio of materials, this is the, what is the Poisson's ratio? The Poisson's ratio is nothing but that is nu equal to minus of epsilon 2 over epsilon 1. That means, as we know that if we are actually pulling a material, that means if assume that we have a bar and this bar is actually pulled in tension, right. That means this is our one direction when we are pulling this material. Now, because we are pulling this material, what will happen? The bar will undergo thinning, that means it will undergo elongation, and it will thin down. That means it will be longer, at the same time it will become slender. That means if this is our direction 1, which is the pulling direction, and this is the direction 2 along which the material is actually getting kind of shrinking or thinning, then the negative of this ratio is actually minus of epsilon 2 over epsilon 1. This is the Poisson's ratio. And because when we are pulling the material, normal materials, when you are pulling them, the strain in the two direction is negative, because it is becoming thinner. That means the epsilon 2 value is negative, and because now epsilon 2 is also negative and here we also have negative, and that actually becomes the Poisson's ratio is a positive material, positive for most of the materials we know. That means all metals, ceramic, composites that we have learned so far, also most of the cellular materials we have learned so far, these have positive Poisson's ratio. but the designing of the cellular solids, because it is a very unique structure, they also allow designing materials with negative Poisson's ratio, as you can see in this case. That means, in these materials if you pull them, the material will not become thinner, it will become thicker. That means, it will have a positive Poisson's ratio, and these materials are typically known as the auxetic materials. That means, auxetic materials are the materials which have a negative Poisson's ratio. Now, as we already learned, so whatever we have learned so far, this is about the deformation of the open cell forms. In case of closed cell forms, the situation is a bit more complicated, because in case of closed cell forms, it is not only about the cell edges we need to consider, we need to also think about the deformation of the faces. That means, for a closed cell form, typically we can see over here, that means we have both the cell edges and the cell faces, and if we can see, that means a unit cell, we can see that the unit cell has a particular length, which is the L, then the thickness of the unit, that means the thickness of the cell edges is the TE, and the thickness of the cell faces is now the TF. And now, what is the value of the TE and the value of the TF? That will actually control the deformation behavior of the closed cell materials, and for that Gibson-Ashby actually kind of proposed one constant, which is the parameter phi. This phi is actually the amount, or this phi parameter actually determines how much of the material is at the cell edges and how much of the material is at the cell faces. So, basically they actually, the Gibson-Ashby actually they take care of the different thickness of the faces and edges in this constant phi. That means, if we know the amount of the material in the cell edges, we can calculate how much of the material in the cell faces, and from that Gibson-Ashby actually proposed that this simple relation for the Young's modulus of the closed cell material. And now we have three different contributions in this expression. The first expression, as you can see over here, that means this first expression, this is the open cell factor. That means, this is the factor that is actually coming from the cell edges, and that is why we see that this is the expression is very similar to the expression for the open cell form, and again this phi here is the amount of material in the cell edges. Now, this second expression is the contribution from the cell faces. That means, as we kind of apply the load, then we have resistance not only from the cell edges, we also have the resistance from the cell faces, and that means, and if the cell face contribution is 1 minus phi, then we have this expression over here. And the third expression over here, this is because of this is the contribution of the fluid that is contained in the cell edges. That means, because it is a closed cell form, we have to assume that the closed cell form, the cells can be either be filled up by a liquid, or in the most normal case it is filled up with a gas. Now, if it is a gas, that means if it is a normal gas like air which is filling up the cell edges, then the contribution of the third term becomes insignificant, because P0 is much lower than ES. So, because P0 is much lower than ES, then actually our contribution of the cell of the pressure which is contained inside the gases becomes insignificant. But if the material, or if the fluid inside the cells is not a gas, rather it is a liquid, then this contribution of the third term is not insignificant, and as a result the liquid of the fluid of the cell, fluid content within the closed cells will also have significant contribution on the overall modulus of the cellular solid. So, that means, according to Gibson-Ashby theory, we have basically three different aspects which control the modulus of the closed cell forms. So, the same thing has been shown over here. That means, in this case, as you can see over here, this is a typical example where, as we are applying the force, we not only have the bending of the cell edges, we also have the stretching. That means, depending upon whether we are applying tension or compression, we also have the stretching of the cell faces, and that will actually provide more resistance to the deformation of the closed cell form, and that will actually lead to higher strength or higher modulus of the closed cell form with respect to the open cell material. Also similar expression has also been proposed for shear modulus, and there also we have the contributions from the cell edges and the cell faces, and again for such cellular materials Gibson has been proposed that the Poisson's ratio is constant, which is not always the case. And there have been advanced models proposed which actually show that the Poisson's ratio depend on the porosity and the architecture, but those are not part of this course, this fundamental course. So basically for now, according to Gibson-Ashby theory, we assume that the Poisson's ratio of the material is constant irrespective of whether it is a closed cell form or open cell form. Now, because the expressions which have been proposed by Gibson and Ashby, they are kind of based upon very simplified assumptions, as we have already seen, that the cells are actually assumed to be cubic in nature, although the real life cells are more complicated, but still these in this plot that you can see over here, in this plot Gibson and Ashby actually try to show that how the real materials they behave with respect to the equations which have been proposed by them. So, the solid curve which you see over here, this solid bold curve, this is actually the expression for the open cell form, and then they have actually proposed two different lines over here for two different values of phi. That means, as we know, phi is the parameter which actually predicts the amount of material in the cell edges. That means, if phi equal to 0.6, that will mean that 60% of the material of the solid in the cellular solid is at the cell edges and 40% is at the cell faces. For phi equal to 0.8, we have 80% in the cell edges and 40% in the cell faces. That means, as the phi value is decreasing, that means we move more from the open cell behavior to the closed cell behavior. So, what we can see over here is that despite the very simple nature of the model proposed by Gibson Ashby, we see that this open cell, in this plot, all the open cell or the open symbols, they correspond to the open cell behavior or the open cell forms. They actually fall pretty much on the line for the open cell form. There is definitely more scatter if we have a closed cell form, but still the Gibson-Ashby theory, they are actually able to predict the behavior of the elastic behavior of the various open and closed cell forms pretty accurately. Also, there is another example that this is another kind of foam or another kind of cellular solids which has been studied extensively. This kind of hollow sphere structures I already showed you, and these hollow sphere structures, they are also supposed to have a closed cell behavior, as we know, because these are again individual cells kind of sintered together. But again, when the elastic behavior of such foams were studied, we can again see that although the foams are as such they are closed cell materials, but still the foam elastic property, they fall pretty well on the line for the open cell behavior. That means again, as we already mentioned, that although there are closed cell forms, because the cell walls are not perfect, the cell faces are not perfect, many of the closed cell forms they also behave similar to the open cell forms, and this is also been confirmed by this plot over here. So, to conclude our today's lecture, we have learned that two elastic moduli are needed for isotropic forms, and if the foam is non-isotropic in nature, that means if the cells are not kind of same in all directions, then we need more elastic constants. As we kind of deform a cellular solid, we have both the bending of the cell edges, and if it is a closed cell form, that will have the kind of the membranes, and these membranes will stage, and because of that the contribution of the strength and stiffness of the foam will increase. In case of in case of foams made by liquid materials or liquid metallurgy route, because when the foam is fabricated, because of surface tension, most of the material actually goes to the cell edges, and in those materials we have very thin cell faces, and because of that the behavior of such materials, they actually follow mostly the behavior of the open cell forms. And also we learned that the modulus of the open and closed cell forms, they depend on the fraction of the solid in the cell faces, which is actually given by the fraction this phi. That means, if phi is the fraction of the material in the cell edges, then 1 minus phi will be the amount of material in the cell faces, and again this parameter will have a significant influence on the modulus of the open and closed cell materials. So, these are the references for this chapter that we covered right now, and in the next lecture we will have in more detail the deformation behavior of the foams under compression. We will study about the elastic plastic behavior and also non-linear elastic behavior under compression behavior. Thank you very much.